In this video, we're going to look at the trends and properties of the group 2 metals. So we're going to look at their atomic radii, ionization energies, and their melting points. And then the properties of group 2 metal compounds. So we're going to look at their reactions with water, their solubilities, and different uses of these compounds. As you go down group 2, the atomic radii get larger. So we can start, beryllium starts with about 0.121 nanometers, and barium ends up with about 0.2 nanometers. So the radii gets larger as you go down. And that's because as you go down the group, you have more electron shells. So for example, beryllium has 2 shells of electrons, magnesium 3, calcium 4, so it would make sense that those atoms would be bigger as you go down the group. As you go down group 2, the ionization energies decrease. So you can see that beryllium has the highest ionization energy, and this decreases as you go down the group. And this is because as you go down the group, you're adding more inner shells of electrons. Because you have more shells of electrons, that means there is more shielding of the outer electrons from the nuclear charge. As well as being more shielded, the outer electrons are also further away from the nucleus. So both of these factors mean that the outer electrons experience less of a nuclear charge the further down the group you go, because there's more shielding of those electrons, greater distance from the nucleus, therefore reduced nuclear charge. That means it's going to be easy to lose those electrons. If those electrons are easy to lose, less energy is required, therefore a lower first ionization energy. And this is why group 2 elements get more reactive as you go down the group, because group 2 elements react by losing electrons. If you've got a lower ionization energy, therefore less energy required, therefore easy to lose them, therefore those metals are more reactive. So for example, calcium is more reactive than magnesium because it has a lower first ionization energy. So we've just said that calcium has got a lower first ionization energy than magnesium, and we can see that here because calcium has got a greater distance between the nucleus and the outer shell compared to magnesium. Calcium has 3 inner shells, shielding the outer electrons from the nuclear charge, while magnesium only has 2 inner shells to do this. The melting points generally decrease as you go down group 2. Magnesium's an exception, and we'll look at that in a moment. So everything in group 2 is a metal, which means it's all metallic bonding. All of the group 2 metals will have a positive 2 charge and 2 delocalized electrons. As you go down the group though, the ions get larger because they've got more shells of electrons like we've already looked at, and the nucleus is further away from the electrons. This means that less energy is required to overcome those metallic bonding. And this is why the melting point decreases as you go down group 2, because whilst all the group 2 elements have got a 2+ charge and 2 delocalized electrons, the metallic bonding gets weaker as you go down because the ions get bigger, the outer electrons, those delocalized electrons, are a greater distance away from the nucleus, therefore a lower force of attraction, those electrostatic forces are weaker, therefore less energy is needed to overcome those metallic bonds. Now, magnesium has a different crystal structure from the other elements in group 2, and this has a big effect on its melting point. Crystal structures is not something which is covered in A-level chemistry. If you do degree level chemistry, you look at all the different types of crystal structures these substances can have, and that will help explain why the melting point is different. But for this topic, you just need to be aware of the general trend that the melting points decrease as you go down group 2. We're now going to look at the reactions of group 2 metals with water. Group 2 metals react by losing electrons, so the group 2 metal is going to form a metal ion with a 2+ charge and 2 electrons. And we can see this in the oxidation states. The metal goes from an oxidation state of 0 to an oxidation state of +2. So for example, magnesium would go to magnesium 2 plus 2 electrons. When group 2 metals react with water, they form a metal hydroxide. Now remember, an OH- ion has a charge of -1. We know our metals have a charge of 2 plus, so we need 2 lots of the OH- ion to form the metal hydroxide. To balance the equation, this means we need to have 2 water molecules, and we also form hydrogen gas. And we can see this in the oxidation states again. The metal starts off with an oxidation state of 0. It will go to an oxidation state of +2. Oxygen has an oxidation state of -2, hydrogen +1, and we've got 2 lots of these. So +2, -2, +1, -2, +1 will give us an overall oxidation state of 0. Therefore, we know this equation is correct. If you're not too sure in oxidation states, you can watch the video from the 3.1.7 topic to refresh yourself on them. So for example then, magnesium plus water would form magnesium hydroxide and hydrogen. You've got to be able to write this equation for any group 2 metal. We're now going to look at the rates of the reactions of these group 2 metals with water. Now all of this is linked to their ionisation energies. Remember earlier on we said that if you have a lower ionisation energy, you're going to be more reactive. So beryllium's going to be the less reactive, and the reactivity is going to increase as we go down the group. So beryllium doesn't react with water. Magnesium does react, but it's a very slow reaction. Calcium reacts at a steady rate. Strontium reacts quite quickly with water. And barium reacts very quickly with water. We're now going to look at the solubility of group 2 metal compounds. The solubility of these compounds depends on the negative ion in that compound. So if the negative ion in that compound has a single charge on it, the solubility increases as you go down the group. If that negative ion has a double charge, the solubility decreases as you go down the group. So for example, if your negative ion was a hydroxide ion, forming a group 2 metal hydroxide, this would be a negative ion with a single charge, because it's a 1- charge. A sulfate ion, forming a metal sulfate, counts as having a double charge, because the charge is 2-. So let's look at the solubilities of the metal hydroxides first. So we know the solubilities of these group 2 metal compounds will increase as you go down the group. Therefore, magnesium at the top of the group will have the least soluble metal hydroxide compound. And so barium hydroxide would be the most soluble. So the solubility increases as you go down the group. Magnesium hydroxide is insoluble, going up to barium hydroxide, which is the most soluble of the group 2 metal hydroxides. For the metal sulfates, we know that the solubility decreases as you go down the group. Therefore, barium sulfate will be the least soluble, it will be insoluble, and magnesium sulfate will be the most soluble. So for group 2 metal sulfates, magnesium is the most soluble, barium is insoluble. We're now going to look at some of the uses of group 2 metals, starting with barium. The fact that barium sulfate is insoluble, like we've just looked at, gives it a really useful application in medicine. X-rays are really good for finding broken bones. The bones absorb the X-rays and therefore they show up on the image. However, they're not very good at finding soft tissues, like the digestive system. So if you need to image the digestive system, you can give somebody what's called a barium meal. It's a barium sulfate suspension, which they then drink. As it goes through the digestive system, it coats the digestive system, And barium sulfate is opaque to X-rays. They can't pass through it. So this means the digestive system will show up on an X-ray. And here's an image showing that. So you can see how the digestive system, not normally visible on an X-ray, will show up if the patient has taken a barium meal, that barium sulfate suspension. It's coated the insides of the digestive system, therefore it shows up on an X-ray. Barium, however, is poisonous. This is why we have to use barium sulfate, and we couldn't use, for example, a different barium compound like barium hydroxide. Because it's insoluble, it forms that suspension and it would pass straight through the body. If it formed a solution, so if it dissolved in water, then it would be absorbed by the body and poison the patient, which is obviously not what we want to happen. So we have to use barium sulfate because it is insoluble. We can also use barium as a test for sulfate ions, which is something you'll have briefly covered in GCSE chemistry. So the first step is to add some acidified barium chloride solution. So the barium would then react with any sulfate ions present, forming barium sulfate. And this would form an insoluble white precipitate, so it'd be quite obvious to see if you formed that, therefore confirming the presence of sulfate ions in your solution. It's really important though that the barium chloride solution is acidified. We do this by commonly mixing it with hydrochloric acid. And this is because there are a lot of carbonate ions in many salt samples. Now, barium will react with carbonate ions to form barium carbonate, which is a white solid, and you can see how that could confuse us with the insoluble white precipitate. But if the barium chloride is acidified, the hydrogen ions will react with the carbonate ions, remembering the hydrogen ions will come from the acid, and that will form water and carbon dioxide gas. So the acidified barium sulfate, the acid, will remove any carbonate ions from that solution, so we know any white precipitate that we see must be barium sulfate, because we know there can't be any barium carbonate left in that sample. We would usually use hydrochloric acid, because there are already chloride ions present in the barium chloride, so we're not introducing any new ions into our test sample. We can't use sulfuric acid, because obviously if we use sulfuric acid, we'd be adding sulfate ions into the solution, therefore compromising the test. We can use magnesium to aid in the extraction of titanium. So the main ore of titanium is titanium dioxide. If we heat this in the presence of chlorine gas, we form titanium chloride. This is then purified by fractional distillation. We then react the titanium chloride with magnesium at about 1000 degrees, and this will give us titanium and magnesium chloride. Now, burning fossil fuels can produce acid rain. This is something you looked at in the alkanes topic of organic chemistry. Fossil fuels contain sulfur impurities. Burning the fossil fuels causes sulfur dioxide to be produced, and the sulfur dioxide can react with water vapour in the clouds to form acid rain. Now we can remove the sulfur dioxide from the gas emissions from burning the fossil fuels by spraying onto these gases a slurry of calcium oxide or calcium carbonate. So a slurry is a bit like a suspension of the solid calcium oxide or the solid calcium carbonate in water, but it's not an aqueous solution. You need to know the equations for this process, but you can see, as we mentioned the slurry earlier, that you've got solid calcium oxide and solid calcium carbonate with water to form that slurry, reacting with the sulfur dioxide gas to produce calcium sulfate, and in the case of the calcium carbonate, the carbon dioxide. Now you'll see that you've got water present on both sides, and that's because we're using it as a slurry rather than an aqueous solution. So you do have to show the water molecules on each side. You can't just cancel them off because it's not solid reacting with the gas. It is this kind of like suspension here so you need to make sure to include the water on both sides of your equation. Be careful with that. Finally, we're going to look at the use of calcium hydroxide and magnesium hydroxide. So calcium hydroxide is used to neutralise acidic soils, so farmers use that to keep the soil pH at a certain level. And magnesium hydroxide can be found in some indigestion tablets to help neutralise stomach acid.